Dear students, our new topic is combination of resistors. In the electrical circuits of radio, television and so many other things, we have to combine two or more resistors in order to get the required current. So we can join two or more resistors lengthwise, or we can join the two or more resistors parallel to one another. The resistors can be combined into two ways. The first one is in series and the second one is in parallel. If you want to increase the total resistance of an electric circuit, we have to connect the resistors in series. If you want to decrease the total resistance of an electric circuit, we have to combine the resistors in parallel. Now we can move to the definitions of series and parallel. In this figure, just take one resistor and take another resistor. Just join one end of the second resistor to the first resistor. If there are more than two resistors, you can join end to end. Thus, we can define the resistors in series as if we connect two or more resistors end to end consecutively, then the resistors are said to be connected in series. I will repeat. If we connect two or more resistors end to end consecutively, then the resistors are connected to be in series. So here you can see that this is the first resistor. The ends are A and B. This is the second resistor. It is represented by R2. Its ends are B and C. And this is the third resistor. Let's see. Here the one end of the second resistor is connected to the one end of the first resistor, and other resistor is connected to the other end of the second resistor. Is it clear? Similarly, we can move to the definition of resistors connected in parallel. If we connect two or more resistors between the two same points, then they are said to be connected in parallel. I repeat, if we connect two or more resistors between two same points, then the resistors are said to be connected in parallel. Here, the 2 points are A and B. The two ends of first resistor R1 is connected between A and B. Here also, the two ends of the second resistor R2 are connected between A and B. Third one also connected between A and B. Let's see how we can find the total resistance or combined resistance when the resistors are connected in series. The combined resistance is also called as equivalent resistance or total resistance, okay, or resultant resistance also. Before writing the derivations, we have to explain the figure. So after writing the heading resistors in series, you have to draw the diagram. This is the circuit diagram. Then once we complete drawing the diagram, we have to explain the figure within a short paragraph. So I'm going to explain how we have to explain the diagram in the introduction part. Consider three resistors of resistances R1, R2 and R3 are connected in series. That is the first sentence you have to write. Consider three resistors of resistances R1, R2 and R3 are connected in series. A potential difference of V volt is applied across the combination. A potential difference of V volt is applied across the combination. See here, three resistors are connected between different points. R1 is connected between A and B, and R2 is connected between B and C, and R3 is connected between C and D. So, since the resistors are connected between different points, the potential difference across each resistor will be different, isn't it? Since the resistors are connected between different points, the potential difference between each resistor will be different. But here, see, the current, let I be the current flowing through the circuit, flowing from the battery. Then there is only one path for the current to pass, isn't it? When this current I reaches this point A, there is no other path to move. So entire current will flow through the same I current will flow through the R1, and it will reach B, and again it flows to the R2 and R3 and reaches to the negative terminal of the battery. In order to measure the current, we have to connect an ammeter in series to the circuit. When you connect the ammeter, make sure that the positive terminal of the ammeter must be connected to the positive terminal of the battery, and negative terminal of the ammeter is connected to the negative terminal of the battery. Then, in order to, if you want to measure the individual potential difference across each resistor, you can connect 3 voltmeters across these resistors. Then, if you connect the first voltmeter, it will read the potential difference across R1. Here, it will read the potential difference across R2, and here R3. Is it clear? Then, what we can write that The individual resistance V1, V2 and V3, the sum of these resistors, the sum of these potential will be equal to the total potential difference of the battery. So that's the first one we have to write. The total potential difference of the battery V equal to individual sum of the individual potential differences V equal to V1 plus V2 plus V3. This is the first equation. Now we have to apply the Ohm's law to each resistor. So V1 can be written as V1 equal to I1 into R1, isn't it? By applying Ohm's law, V1 can be written as I1 into R1. Since the current flowing through the circuit is same, now I need to mention it one by I1. We can simply write V1 equal to I into R1. Similarly, V2 can be written as I into R2, and V3 can be written as I into R3. So these are the second equation. Now look at second equation. Anyway, we have connected all these resistors in series. There will be a resultant resistor. This resultant resistance or resistor can be represented as Rs. Rs is the total resistance of the combination, and we know that I is the current flowing through the combination, and total potential difference is V, that is provided by the battery. Then applying Ohm's law again to the total measurements, then we will get V can be written as V equal to I into Rs. V equal to I into Rs. This is general equation, that is the total potential difference equal to total current into total resistance. This can be represented as third equation. Now we have to substitute equation 2 and 3 in equation 1. Then how do we get V equal to V1 plus V2 plus V3? Isn't it? Instead of V, what we can substitute? V equal to I into Rs. Then I into Rs equal to, substitute these equations in V1 in the place of V1, V2 and V3. So I into R1 plus I into R2 plus into R3. Just observe this equation. You can find that I is common on both sides. So we can take I outside. Rs equal to, I can be taken outside. I into R1 plus R2 plus R3. Simply we can cancel this I from this equation. So what will get? R is equal to R1 plus R2 plus R3. This is the total resistance when we connect 3 or more resistors in series combination. The equivalent resistance when the 2 or more resistors are connected in series is the sum of individual resistances. It's easy for you to calculate the total resistance when we connect number of resistance in series. Just add the individual resistance, you will get the total resistance. R is equal to R1 plus R2 plus R3. In the case of 3, otherwise we can put R etc. Now we can move to the derivation of resistors in parallel. Once you study the derivation of first, once you know how to structure a derivation, then it will be easy for you to write yourself. First we have to draw the diagram. In this diagram, 3 resistors are there, R1, R2 and R3, and all the resistors are connected in parallel between the points A and B. So here the difference is all the resistors are connected between the same points A and B. Then now we can start our derivation. First we have to explain the figure. So consider 3 resistors of resistances R1, R2 and R3 are connected in parallel as shown in the figure. Okay. Then let I be the current flowing through the circuit. A potential difference of V volt is applied across the combination. Now we have completed these 3 and potential difference and current also. Then a ammeter is connected in series to the circuit in order to read the current flowing through the total current flowing through the circuit. When we compare this derivation with the previous one, we can see that the potential difference across each resistance are same, but the current flowing through the each resistance are different. That's the main difference we can see when you compare the studies with the resistors in series and parallel. Now we can apply the Ohm's law to the each current. So I1 can be represented as I equal to V by R1. Why we are not using V1? The reason is potential difference across each resistor will be same. So V1, V2, V3 can be taken as V only. Similarly, I2 can be written as V by R2 and I3 can be written as V by R3. These three equations can be written as equation 2 and this will be the first equation. Now, let RP is the total or equivalent resistance when the resistors are connected in parallel and total current is represented by I and the total potential difference is represented by V. Then again apply the Ohm's law to the total values. Then I will be equal to, here we have to substitute for I. So we have written the individual equations for I1, I2, I3. Then what is remaining here? I only. So we can apply the Ohm's law for the total current I. So I can written as I equal to V by total potential difference divided by total resistance RP. This is our third equation. Okay, now we can substitute equation 2 and 3 in equation 1. The equation 1 is I equal to I1 plus I2 plus I3. Instead of I, we have to write the total current, Ohm's law. Then V by RP equal to, instead of I1, we can substitute V by R1. Similarly, V by R2 and V by R3. Here you can see that V is common taken. So we can take V from the RHS outside. So V by RP equal to V into 1 by R1 plus 1 by R2 plus 1 by R3. So we can cancel both V from each side. Then what we will find equation 1 by RP equal to 1 by R1 plus 1 by R2 plus 1 by R3. So this is our final equation. So what we can say, the reciprocal of equivalent resistance when a number of resistors are connected in parallel is equal to the sum of reciprocals of individual resistances. I will repeat, the reciprocal of equivalent resistance or total resistance when resistors are connected in parallel is equal to the sum of reciprocals of individual resistance.